We now know how an inductor acts in a circuit with a change in current. So let's analyze the function of this inductor along with the resistor. And we've done similar things, similar analysis for a capacitor, an RC circuit, but the results are different because it turns out an inductor and a capacitor function very differently in a circuit. So we start by switching up the switch into this position so we have a circuit, and immediately the current would like to rise to its maximum value, would like to do it instantly. However, it can't, because we know an inductor will induce an EMF in itself, and that self-induced EMF is dependent on the rate at which that current changes. So here's the direction of the self-induced EMF. EMF self-induced. I usually won't use that subscript, but there it is for now for our functional understanding. So di dt is not equal to infinity. It can't be equal to infinity, considering what we just said, because that would result in an infinite EMF induced. EMF is minus L di dt. Di dt can't be of arbitrary large size, because this times L is just the EMF, and that would make it go to infinity if di dt went toward infinity. The di dt is really dependent on the L, namely the product of these two is the EMF induced, and that's limited by the source, isn't it? So VAB is equal to L di dt. VBC, VB with respect to C, just the resistive circuit, just IR. So let's now do a Kirchhoff loop around this whole circuit. Here's where it gets practical. So we have EMF minus L di dt, plus to minus. It's a drop in potential. Minus IR equals 0. There's the whole loop. So let's algebraically solve for di dt, and the algebra would give us EMF over L minus IR over L. You can work that algebra out if necessary. So there it is. Now, the initial current. If you haven't picked up on this yet, what must the initial current be? In order for the initial current to be anything other than 0, it means that it would have to have an infinite di dt. So it has to be 0. Same thing as saying in mechanics, we start with an object of mass m from rest, and we apply a force. What's the initial velocity? Well, you know it's 0. Because the only way for it not to be 0 is for the acceleration to be infinite, which means you need an infinite force, which would of course obliterate the object if it's an object that's made in this universe, because you got matter, and matter doesn't have the ability to withstand an infinite force. The best you could say is it would turn it into a plasma in the attempt. Anyway, the initial current is 0 because di dt can't be infinity. Di dt is actually just EMF over L. And you know that because the I is 0, the initial current. So this whole thing is gone. Di dt is EMF over L. This is coming together for us. At steady state, what happens? Steady state means you've got quiescent conditions or equilibrium conditions. You've waited long enough for things to settle out. When things have settled out, there is no longer any change. The di dt is equal to 0. There is no di dt, which means that this inductor, no longer having a change in current, acts just like a 0 ohm resistor, and it's just a resistive circuit at that point. So di dt equals 0, which is equal to EMF over L minus IR over L. All right, well now we can multiply both sides by L. We have EMF is equal to IR. So I steady state acts just like a regular resistive circuit, EMF over R. Well, now that we have the beginning and ending conditions understood, which is usually the easy part, let's do the, the interesting part, the intermediate values, function of time. So let's handle the math here. di dt is EMF over the inductance minus IR over the inductance. So So there's our differential equation that we need to solve. And so let's do it. First of all, combine EMF minus IR over L. Now we'll rearrange. What do we have to rearrange? We got to separate the variables. So let's go ahead and do that. So DI, divide by this side, bring the I over here. So DI over EMF minus R is equal to DT over L. Good step. I'm going to multiply both sides by R to get I by itself, so I can at least more easily see what the integral is going to be. DI over EMF minus R minus I, should be the same thing, right? Is equal to R over L dt. So now we're ready to integrate. From 0 to I of the first part equals minus R over L integral 0 to T dt. So that's natural log of I minus EMF over R equals minus R over LT. And let's go ahead and do natural log of I minus EMF over R over minus EMF over R equals minus R over LT. Let's E both sides. And we have this result. And now we're just going to multiply both sides by the minus EMF over R. So there we have this part. And now we can rearrange and factor the EMF over R to give us a result that looks very similar to the RC circuit form, which was maximum quantity, 1 minus E to the minus, well, in RC circuit, it was E to the minus T over RC. Now we have the same kind of form, but it's 1 minus E to the minus R over LT. Well, remember the time constant for an RC circuit was, we had minus T over RC, and it was an RC time constant. So it was what was in the denominator that was the time constant. What's in the denominator here? Well, the numerator is R over L, so the denominator is L over R. So that is the time constant. Now, to be careful about this, which we'll do next, the form of this equation may not have the same exact logic as the RC. In other words, what's maximum and what's minimum. So let's now check that out. Well, now let's graph it. We have an increasing current. So remember, the current starts at 0 and it goes up. It starts at 0 because di dt cannot be infinity. It's the only way it could have a non-zero starting point, which is an insane thought. It's a thought experiment. You can't have, actual infinities. When you think they actually are happening, you're usually wrong. Probably always. Well, so here's our current. The equation we just solved gives us this. It starts at minimum and goes to maximum. The maximum value is when there's no change in current, and you just end up with a resistive circuit, EMF over R. This is the one-time constant, L over R. So we know we have most of the current already flowing in the circuit at one-time constant. Now let's discharge it. When we discharge, here's the circuit. We flip the switch the other way. It eliminates the EMF source. The EMF source is really now this inductor. Remember, the current in the inductor cannot change instantaneously. So the current is just what it was before. That's really huge in this inductor consideration. But let's just look at what the current, the Kirchhoff loop becomes. As we go clockwise around here, we're going to have, immediately, we have an EMF induced in this direction. What you notice is the EMF induces flips around spontaneously. It was going the other way. Now it's going from right to left because it's got to be now the source of what keeps its own current flowing. So here's the Kirchhoff loop. L di dt, it's a rise. Rises across here. Minus IR equals 0. Very simple Kirchhoff loop. Important consideration, di dt. Di dt is getting smaller. So di dt itself is negative. I is going down. So that makes our equation L di dt equals minus IR. And di dt equals minus R over L dt. Now we can integrate both sides from what it was, the initial condition, which is the maximum current flowing around the circuit. Actually, it was what it was over here. We flip the switch, that current is maintaining itself, and then goes to a smaller value a little bit later. So that's what the limits mean. Minus R over L from 0 to the time at which you arrive at that intermediate current. So ln of I over I0 equals minus R over LT. We're going to E both sides, which gives us that intermediate current over I0. So let's just multiply by I0. E to the minus R over LT. And that I0 is the EMF over R, because it's just like a resistive circuit, the maximum value of current. And that's our result. So that is the current that we get during discharge. Notice that if you're observing, the form is opposite of what it was for a capacitor. Charge discharge is like discharge charge now. Okay, so let's graph the current as it's discharging. Really, it's the inductor that's discharging. So we have the current going from its maximum value. Notice the same direction. That's really hugely important. In an RC circuit, after it was fully charged, the current flipped directions and went the opposite way. Here it's going the same way. Because think about how much dIdt you would need to reverse current direction. And moreover, of course, at the end of the charge phase, the current is actually at its maximum value. So to flip around would certainly be an obvious infinity dIdt. So you can't have that, so the current maintains what it was doing and diminishes off as this indicates. So maximum value of EMF over R, and at one time constant, L over R time constant, you get to this small value of the initial current. If you look at the voltage, consider the voltage across the inductor. During charging, initially we had maximum value, positive, and that diminished down to 0 as the dIdt reduced. Now why does it reduce? Because as the current increases, the voltage drop across the resistor increases, so it's fighting the source, and so the voltage across the inductor doesn't have to do as big of a job because the resistor is doing a lot of it, right? And then, however, as soon as you flip the switch, now it's all up to the inductor to produce the voltage that drives the current. And so the voltage that drives the current is suddenly in the opposite direction. So it's now becoming the source to drive the current through the system, through the resistor. So that voltage is got a negative EMF e to the minus R over LT. So notice the form, the voltage during charging, EMF maximum e to the minus R over LT. Then during discharging, minus EMF e to the minus R over LT. So there is the summary of all the voltages and currents pertinent for an RL circuit. And of course, you can make the extension to what the voltage is across the resistor. The current in the resistor and the inductor are, of course, the same. Lastly, let's consider power. And so as we're going to charge a circuit, EMF equals the IR plus the LdIdt. And to get power, you just multiply by I to have the dimensions of power. So we have EMF times I is equal to I squared R plus LIdIdt. And so each one of these things can be specified. The EMF times I is what's delivered by the source. The I squared R is dissipated in the resistor, and the LIdIdt is the power delivered to the inductor that then gets stored as potential energy, etc. So that will be a conclusion to our RL circuit initial considerations, and maybe we'll just do another one that adds just a little bit of complexity to it.